Hey everyone, in this mini lecture we're going to look at the transport of energy and specifically heat transfer in just a moment. First, I want to look at a quick diagram. This is going to be the diagram of a turbine, where turbine blades. So here it is, rough diagram. And here we have steam going in. So I'll say steam in right there, and right here we'll have steam out. All right, steam out. So the steam going in, as shown in this figure right here, can push on the turbine blades. Here's the turbine blades. It can push on the turbine blades, causing the turbine's rotor to spin. And then this produces a desired effect. And for us, maybe this will be about 250 kilowatts, right? So this situation can occur. The flowing steam can cause a turbine shaft to spin as it impinges on the turbine's blades. All right, so showing this, let's look at the three general ways of energy transport. Alright, so energy transport in three general ways. The first way is by heat transfer. The next way is through work. And then we have what's called mass transfer. So through heat transfer, through work, and through mass transfer are the three general ways of energy transport. So we're going to look at heat transfer. All right. So let's go ahead and identify this one, heat transfer. So the transfer of energy via heat transfer is the movement of energy. So it's the movement of energy, and it's caused by a temperature difference. And this temperature difference is between the two systems. Right? So we'll use Q. Q will be the amount of heat transfer, or it could be the rate of heat transfer. And in looking at this, a quick little diagram could be shown for us. This way we have some water in here, and the water is at 20 degrees Celsius, and then there's some metal on top of it that's 100 degrees Celsius. Alright, and then I'll draw the second diagram, the water again, and this is at 40 degrees Celsius, and maybe the metal is now submerged and at 40 degrees Celsius. So the placement of a hot object, so that metal, into cool water, which was 20 degrees Celsius, causes energy to be transferred in the form of heat from that hot object, from the 100 degrees Celsius metal to the 20 degrees Celsius water. So this happens until thermal equilibrium is reached, which is shown in this second diagram. Alright, so in talking more about heat transfer, there are some modes of heat transfer. Well, we have what's called conduction, we have what's called convection, and we also have what's called radiation. So conduction, convection, and radiation. All right, we're looking at conduction right now. So conduction is the process of transferring energy from one atom or molecule directly to another, right? So from one atom or molecule directly to another atom or molecule. What do we need for conduction? We need a temperature difference, right? A temperature difference between the molecules. And we also need direct contact between the molecules. All right, so this is what's needed. All right, so that'll move us into heat transfer, and we're going to look at first the formula, and this formula is known as Fourier's Law for heat transfer. So we have Q, and I'll write sub COND for conduction. It's equal to negative K times A times dt over dx. All right, so what are these? K is the thermal conductivity, and that's usually given in watts per meters times Kelvin, or watts per meters times Celsius. We could use that. Okay, next A is of course the area, but it's the area that's perpendicular to the direction of heat transfer. All right, so area perpendicular to the direction of heat transfer. And then lastly, we have what you probably remember from looking at your calculus, dt over dx. So this is just for us, nothing too complex, the rate of change of the temperature, and this is with respect to position x, with respect to the position, which for us would be the x. Sometimes they'll refer to it in other textbooks as the temperature gradient. The temperature gradient is just approximately delta T over delta X, right? The change in T over the change in X. All right, let's go ahead and take a look at an example, and we'll see how this works for us. So what I'm going to do is draw a diagram. Usually thermal problems come with a diagram. If not, then they'll give you lots of details. So this is a wall, and I'll draw the wall. It's a brick wall, and here's the heat flow in that direction. It's about 10 centimeters. Okay, and here we have inside of this building, perhaps, is 20 degrees Celsius, and we'll say outside is negative 5 degrees Celsius. All right, so we have the heat transfer that's going to go on here through conduction, through this wall, right? So the heat will transfer via conduction through a wall from an area with a higher temperature to an area with a cooler temperature. So from the 20 degrees Celsius area to the negative 5 degrees Celsius area. All right, so what's given? Everything that's given. So we'll call T sub 1 20 degrees Celsius, T sub 2 is the -5 degrees Celsius, right? All right, then we have x sub 2 minus x sub 1. That's going to be 10 centimeters, or we'll change it to 0.10 meters. All right, and then the area is 8 meters squared. All right, 8 meters squared. And then we have our K is 0.70 watts per meter times degrees Celsius. So this is all that's given to us already in the problem, right? It's already given to us. It'll be either given through the diagram, through the picture or figure that's shown, or in the actual wording of the problem itself. Right now in this mini lecture, I'm just throwing it all out there, but you'll find it in your analysis of the problem. All right, so we have Q conduction is equal to -K times A times dt over dx, right? So dt over dx is basically T sub 2, what I just spoke about earlier, that temperature gradient, the change in temperature over the change in x. So T sub 2 minus T sub 1 over x sub 2 minus x sub 1. So what does that get us? That gets us, crunching the numbers in, the -5 minus 20 and x2 minus x1 up there was already given us as 10 centimeters, which is 0.10 meters. Then doing that number crunching, we get about 250 degrees Celsius per meter. All right, so now again, Q conduction is equal to, that K value is -0.70 watts per meter times degrees Celsius. The area we found to be 8 meters squared, and dt over dx we calculated as 250 degrees Celsius per meter. All right, and that boils down to about -1400 watts, which is also equal to -1.40 kilowatts. -1.40 kilowatts. All right, so this was an example of heat transfer through conduction. All right, so the next type of heat transfer we'll look at is through convection. So heat transfer, heat convection, so it will be the energy that is transferred between a solid surface and a moving fluid, right? So again, it's energy transferred between a solid surface and a moving fluid, and that moving fluid is in contact with the surface. So that is in contact with the surface. All right, so the processes of heat convection. So for this, heat conduction between the molecules in the moving fluid and the solid surface, so that's part of it, and then advection from the motions of the fluid. So here we have Q convection equals H times A times the quantity of T sub F minus T sub S. All right, this is also known as Newton's law of cooling. Newton's law of cooling. So the H for us is going to be the convection heat transfer coefficient. Again, it's the convection heat transfer coefficient. All right, the A will be surface area. A is the surface area, and that's the surface area that's in contact with the fluid. T sub S is the surface temperature, and T sub F, that is the fluid temperature. And this will be the fluid temperature that's well away from the surface, because the fluid temperature on the surface will equal the surface temperature due to conduction. So this fluid temperature is the fluid temperature well away from the surface. All right, let's hop into an example. And I'll always want to start off with the diagram that they'll likely give us, but again, if not, they'll give us plenty of details on it. So this is going to be the diagram of a furnace. All right, so some simple furnace. Inside we have the fire going on there. All right, and there's a little opening at the top, and then we have air at about 20 degrees Celsius going over this warm furnace. The furnace, we'll say, is about 70 degrees Celsius. And as the air passes over, the air will be greater than 20 degrees Celsius. All right, so the cool air will heat up as it flows over this very warm surface, and it does so via heat convection. All right, so what are we given? This will be what we're given in the word problem or in the diagram. We're given T sub F is 20 degrees Celsius. T sub S is 70 degrees Celsius. H is 155 watts per meter squared times K. And this convection heat transfer coefficient is not something very easy to analyze, right? You'll have to take a whole course in heat transfer to analyze that further and how we come up with that. A is 3.5 meters squared. All right, all this information will be given in the word problem. All right, so here's the solution. The solution is to go ahead and use the formula, Newton's law of cooling, and this is going to be H times A T sub F minus T sub S. All right, and it's equal to 155 watts per meter squared times K times 3.5 meters squared times 20 minus 70, and this is degrees Celsius. Again, just some number crunching in your calculator, and you get about negative 27,100 watts. So for us, that's equal to about negative 27.1 kilowatts. All right, so the negative sign in our answer indicates that the heat is leaving the surface. The heat is leaving the surface. The next means of heat transfer is through radiation. Through radiation, energy is transferred via photons, right? Via photons, or what we call electromagnetic waves. So as shown in the Stefan-Boltzmann law, it's highly dependent on temperature. So we have Q, and I'll say emit, E-M-I-T, equals sigma times A times T sub S to the fourth power. So A is the surface area. Sigma will be the Stefan-Boltzmann constant. The Stefan-Boltzmann constant, which is 5.67 times 10 to the negative 8 watts per meter times K to the fourth, which we can make 0.1714 times 10 to the negative 8 BTUs per H times feet squared times R to the fourth. All right, and then T sub S is the temperature at the surface. Temperature at the surface. All right, so this is the maximum rate of heat transfer from a surface. So we can go further and say, let's look at the net rate of radiation heat transfer between a surface and surroundings. So again, we're looking to now look at the net rate of radiation heat transfer between a surface and surroundings. And we'll use Q rad, R-A-D. And that's equal to negative E sigma T sub S to the fourth minus T sub SURR to the fourth. And that E is the emissivity of the surface. The emissivity of our surface. And you can think of emissivity of the surface as the efficiency of a surface at emitting radiation. So again, the emissivity of surface can be thought of as the efficiency of a surface at emitting radiation. So we have the negative sign, and that's used to maintain consistency with heat transfer sign convention, and that's usually described later on in this course. And of course we have T sub SURR, and then that's just the temperature of the surroundings, right? Because the surroundings are radiating heat to the surface as well. All right, so let's take a look at an example here. I'm just gonna draw just a crude picture of some people standing, let's say they're standing outside waiting for the light rail, some type of subway train that appears above land as well. So some light rail system outside, and outside may be negative 2 degrees Celsius, but then there are these big giant lamps, these big giant heat lamps, right, to warm the people up. That's at 250 degrees Celsius. All right, so we're given, either through the diagram or through the actual word problem, that the area is 0.25 meters squared. T sub S is equal to 250 degrees Celsius, which is about 523 Kelvin. T surrounding is -2 degrees Celsius, which is 271 Kelvin. And then our emissivity of the surface, that E value is 0.92. All right, so the heat lamps for us in this diagram use radiactive heat transfer to keep people warm in this outdoor setting while they're waiting for a train or something like that. All right, so let's take a look at the solution. So the solution. So we're trying to figure out that net rate of radiation heat transfer between the surface and surroundings. So that's going to be using our formula. All right, so our formula, as you recall, is as such. And then we'll just substitute in -0.92 times 5.67 times 10 to the -8 watts per meter squared times K to the 4th. And this is times 0.25 meters squared. And this is times 523. Sorry, it should be 23 Kelvin. And that's to the 4th. And then this is minus 271 Kelvin to the 4th. And all of that is equal to about -905 watts. -905 watts. So the negative sign here indicates that heat is leaving the lamp. Our heat is leaving the lamp. Alright, so heat transfer is what we've been discussing. Heat transfer through conduction, convection, and radiation. So we can say that the total amount of heat transfer experienced by a system is the sum of the contributions from the 3 heat transfer mechanisms. So that total amount is the sum of the 3 heat transfer mechanisms. So Q conduction plus Q convection and Q radiation. All right. So the sum of those 3 will give us the total amount of heat transfer experienced by a system. Here, looking at 2 systems, we have Q equals +10 kilojoules, and on the right Q equals -10 kilojoules. So the sign, as you see, the sign convention for heat transfer is that heat transfer into a system is positive, and then heat transfer out of a system is negative.